A galaxy so massive, it breaks every rule we thought we understood. Scientists found it by accident, hidden in old telescope data because it was too large for anyone to notice. This thing stretches so far across space that light takes millions of years just to cross from one edge to the other. And sitting at its heart is a black hole that should not exist, feeding on matter and blasting jets of energy across distances that make our entire galaxy look like a speck of dust. February 2022 changed everything astronomers thought they knew about cosmic limits. A team in the Netherlands was scanning radio telescope data when they spotted something impossible. Two massive plumes of energy stretched across space farther than any structure ever recorded. The discovery happened almost by accident. Scientists were using the low-frequency array, a telescope network spread across Europe, mapping the northern sky in wavelengths invisible to human eyes. They expected to find typical radio galaxies, the kind with jets shooting a few million light-years into space. What they found instead was Alcyoneus. This galaxy had been sitting in telescope data for years. Nobody noticed it because its edges reached so far that earlier surveys cut them off. Think of trying to photograph a mountain when you are standing on it. You capture rocks and trees, but never see the full peak. That is what happened here. The radio lobes, twin structures of superheated plasma, ejected from the galactic core, measured 8 million light-years each. Together, they spanned 16 million light-years from tip to tip. For comparison, our Milky Way stretches about 100,000 light-years across. You could line up 160 Milky Way galaxies between Alcyoneus's two edges. The previous record holder, IC 1101, reaches roughly 6 million light-years in diameter at its widest point. Alcyoneus shattered that record. It became nearly 3 times wider than what scientists believed was possible. The discovery paper, published in Astronomy and Astrophysics, confirmed the measurements. Multiple research teams verified the findings using independent data. This was not a mistake. The galaxy sat 3 billion light-years away in the constellation Lynx, and its scale defied every model of galactic growth. Astronomers named it after a giant from Greek mythology, the king who fought Hercules. The name fits. This cosmic titan makes other galaxies look like pebbles. But here is what disturbed scientists most. Alcyoneus appeared completely ordinary in every other way. Its central black hole measured 400 million times the mass of our star. Large, but not exceptional. The galaxy itself contained roughly 240 billion times our star's mass. Again, impressive but not record-breaking. Other galaxies with similar cores and masses barely reached 1/10 this size. Something allowed Alcyoneus to grow far beyond normal limits. Scientists have theories about lower density environments or cosmic web filaments feeding its expansion, but confirmed answers remain elusive. What makes a galaxy grow this large when others with identical properties stay small? The answer might change everything we understand about cosmic structure formation. Light travels at 186,000 miles every single second. In 1 year, light covers nearly 6 trillion miles. Astronomers call this distance a light year. Now multiply that 6 trillion miles by 16 million. That number has so many zeros your mind cannot process it. Alcyoneus spans a distance of approximately 96 sextillion miles from one end to the other. Writing out that number requires 23 digits. Let me give you something your brain can actually picture. If you could shrink our entire galaxy down to the size of a penny, Alcyoneus would stretch longer than 4 football fields placed end to end. Every star you see in the night sky, every nebula, every planet, every black hole in our cosmic neighborhood compressed into a copper coin. Now scatter 160 of those coins in a line. That visualization still fails to capture the reality because space between these coins would remain empty. But Alcyoneus fills its space with jets of plasma, radiation, and magnetic fields. Here is another way to understand it. Light, leaving one edge of Alcyoneus, takes 16 million years to reach the opposite edge. Humans did not exist 16 million years ago. Our earliest ancestors were still millions of years from standing upright. When light began its journey across Alcyoneus, Earth was populated by creatures we would not recognize. That light is still traveling right now, crossing the galaxy's interior, and will continue for millions more years before reaching the far side. The galaxy exists 3 billion light-years from Earth. This means we see Alcyoneus as it appeared 3 billion years ago. Back then, Earth's surface was covered in bacteria and simple organisms. Complex life had not yet evolved. The light hitting our telescopes today left Alcyoneus when the universe looked completely different. The galaxy might have changed dramatically since then. It could have collided with neighbors, absorbed smaller galaxies, or shifted position. We cannot know its current state. We observe ancient history, frozen in starlight. Scientists measure these distances using redshift, the stretching of light waves as space itself expands. The more space between us and an object, the more its light shifts toward red wavelengths. Alcyoneus shows a redshift value that places it firmly in the distant cosmos. Multiple measurements confirm this distance. The numbers check out. This is not measurement error. The galaxy truly spans 16 million light-years. But distances this large create strange questions. Can we even call something this spread out a single galaxy anymore? Where do its true boundaries lie? For decades, IC 1101 ruled as the undisputed champion. Discovered in 1790 by William Herschel, this supergiant elliptical galaxy sat at the heart of the Abell 2029 galaxy cluster. Its golden glow marked it as a cosmic elder, a structure packed with ancient stars. Astronomers measured its halo, extending 2 million light-years from the core. Adding both sides together gave IC 1101 a diameter around 6 million light-years. Nothing came close. The galaxy dominated every list of cosmic records. Largest galaxy by stellar extent, most massive elliptical structure, biggest galactic core ever measured. Scientists wrote papers analyzing its properties for 40 years. It became the standard against which all other galaxies were compared. When students learned about extreme cosmic structures, IC 1101 appeared in every textbook. Its reign seemed permanent. Then Alcyoneus appeared and changed everything. The new discovery did not just edge past IC 1101. It obliterated the old record by over 2.5 times. Imagine thinking you built the tallest building on Earth, then discovering someone else constructed one 3 times higher. That is how astronomers felt. The shift happened almost overnight. Publications had to update. Documentaries became outdated. The cosmic hierarchy restructured itself around new data. But IC 1101 did not lose all its records. In terms of stellar content, the galaxy still wins. Alcyoneus reaches farther through space because of its radio lobes, structures made of plasma and magnetic fields rather than stars. IC 1101 contains a denser concentration of actual stellar material. Its core remains the largest ever found, measuring 13,700 light-years across. That core alone could swallow dozens of galaxies our size. The supermassive black hole at its center weighs between 50 and 70 billion times our star's mass, one of the heaviest known. The competition between these two titans highlights a problem in astronomy. How do we measure a galaxy's true size? Should we count only the stars? Should we include the halo of dim light surrounding them? What about radio emissions extending millions of light-years beyond visible matter? Different measurement methods produce different winners. By some metrics, IC 1101 still claims the throne. By others, Alcyoneus dominates completely. Both galaxies share one disturbing feature: they should not exist. Standard cosmological models struggle to explain how structures this massive formed in the time available since the Big Bang. The universe is only 13.8 billion years old. building something this large requires billions of years of continuous growth. Yet somehow, against all odds, these cosmic monsters assembled themselves, and something even stranger powers their impossible size. IC 1101 contains approximately 100 trillion stars. Let that number settle in your mind. Our galaxy hosts roughly 400 billion stars, and we consider that enormous. IC 1101 holds 250 times more stars than our entire cosmic neighborhood. Every single point of light you see in the night sky belongs to our galaxy. Now imagine 250 separate galaxies of that same size, then crush them all together into one massive structure. That is IC 1101. Try counting to 100 trillion. If you counted one number every second, without stopping, never sleeping, never eating, never pausing, you would need over 3 million years to finish. Humans have only existed as a species for roughly 300,000 years. You would need 10 complete human evolutionary cycles just to count the stars in this single galaxy. The task is meaningless. Our brains cannot truly grasp numbers this large. Each of those 100 trillion stars potentially hosts planets. Conservative estimates suggest most stars have at least one planet. That means IC 1101 could contain 100 trillion planets or more. Even if only a tiny fraction of those planets could support life, we are still talking about billions of possible worlds. The galaxy might contain more habitable planets than there are humans who have ever lived on Earth. Entire civilizations could rise, flourish, and fall in IC 1101 without ever knowing about the trillions of other stars surrounding them. The stars themselves are ancient. Most formed over 7 billion years ago, making them nearly twice as old as our own star. They burn with a golden yellow light that comes from high metal content. In astronomy, anything heavier than hydrogen and helium counts as a metal. These metals formed inside earlier generations of stars that exploded as supernovae, scattering heavy elements across space. The fact that IC 1101 stars contain so many metals tells us they formed from recycled material. Multiple generations of stellar life and death preceded them. Very few new stars form in IC 1101 today. The galaxy exhausted most of its gas supply long ago. Starbirth requires cold molecular gas clouds, where gravity can pull material together into newborn stars. IC 1101 converted nearly all its gas into stars billions of years ago. What remains is a population of aging stars slowly burning through their fuel. The galaxy is dying, not dead, but fading. In another few billion years, the dimmest stars will wink out first, and the galaxy will grow darker. But this dying galaxy still devours. It captures smaller galaxies that wander too close, absorbing their stars and adding to its collection. Growth through cannibalism keeps IC 1101 alive, even as its own star formation fades to nothing. And the force controlling all those trillions of stars sits at the very center, waiting in darkness. At the heart of IC 1101 lies something physics says should not be possible. A black hole weighing between 50 and 70 billion times the mass of our star. To put this in perspective, the black hole at our galaxy's center weighs about 4 million times our star's mass. The monster in IC 1101 is 17,000 times heavier. If you replaced our galaxy's black hole with IC 1101's, the gravitational influence would reach halfway across our galaxy, tearing apart stars and warping space in ways that would make life impossible. Black holes form when massive stars collapse. A typical stellar black hole weighs 5 to 50 times our star's mass. Supermassive black holes at galactic centers weigh millions to billions of times more. Scientists believe these giants grew by swallowing gas, dust, and stars over billions of years. They also merge when galaxies collide, combining their masses into even larger monsters. This process explains most supermassive black holes we observe, but IC 1101's black hole sits near the theoretical upper limit. Cosmologists calculated maximum possible black hole masses based on the universe's age and the amount of material available. These calculations suggest black holes cannot grow much larger than 100 billion times our star's mass before running out of food. IC 1101's black hole already reached halfway to that limit. Scientists call it overmassive. It grew too large too quickly, and they cannot fully explain how. The black hole powers a massive radio source catalogued as PKS 1508 plus 059. This means the black hole is actively feeding. As matter falls toward the event horizon, it accelerates to incredible speeds, heating up and emitting radiation. Some of that material never crosses the event horizon. Instead, powerful magnetic fields channel it into two narrow jets shooting perpendicular to the accretion disk. These jets travel at 98% the speed of light, carrying energy millions of light years into space. The black hole consumes roughly 450 times our star's mass every single year. That is more than one entire star's worth of mass per day. Where does all that material come from? The galaxy's core contains vast clouds of gas, but also entire stars that wander too close. The black hole's gravity tears them apart in a process called spaghettification. The star stretches into a long stream of matter that spirals into the black hole's accretion disk. The process releases tremendous energy visible across electromagnetic spectrum. Observing this black hole directly remains impossible. It sits over 1 billion light-years away, and black holes emit no light themselves. We detect them through their effects on surrounding matter and through gravitational measurements. Scientists study how stars near the core move, calculating the central mass based on their velocities. The numbers consistently point to something unimaginably dense and massive. But if this black hole disturbs scientists, what Alcyonius does with its central engine will terrify you. Alcyonius exists in wavelengths your eyes cannot see. If you pointed the most powerful optical telescope at its location, you would find a faint elliptical galaxy that looks entirely unremarkable. Nothing about its visible appearance suggests anything unusual. The true nature of Alcyonius only reveals itself when you look in radio wavelengths, the same type of waves your car radio receives but at different frequencies. What appears in those radio images changes everything. Two enormous lobes extend from opposite sides of the galaxy. These structures glow bright in radio observations, each one stretching 8 million light-years into space. The lobes form when jets of superheated plasma shoot from the black hole's poles at nearly the speed of light. As these jets travel outward, they push through the thin gas between galaxies. Eventually, they slow down, spreading out into massive clouds of particles and magnetic fields. These clouds emit radio waves through a process called synchrotron radiation. Synchrotron radiation happens when electrons spiral around magnetic field lines at relativistic speeds. The electrons lose energy by emitting photons, primarily in radio wavelengths. The process is incredibly efficient, allowing us to detect these lobes across billions of light-years of space. The total radio power output from Alcyonius measures around 100 million watts. That number has 26 digits. It represents more power than trillions of stars combined. The Low-Frequency Array telescope detected Alcyonius by scanning the sky at frequencies between 120 and 168 MHz. These low frequencies penetrate through dust and reveal structures invisible to other instruments. The telescope array spans multiple countries, with individual stations in the Netherlands, Germany, Poland, France, and several other European nations. By combining signals from all these stations, astronomers created a virtual telescope thousands of miles wide. This technique, called interferometry, provides resolution impossible from any single instrument. The Discovery team processed petabytes of data searching for giant radio galaxies. They found dozens of large structures, but Alcyonius stood apart. Its lobes extended so far that earlier surveys missed them because they exceeded the field of view. Imagine trying to photograph a whale. when you can only capture a few feet at a time. Previous observations saw the galaxy's center and parts of the jets, but never connected them to the distant lobes. The complete picture only emerged when astronomers stepped back and looked at a much wider region of sky. Radio galaxies, like Alcyoneus, are relatively common. Astronomers have catalogued thousands of them, but most reach only a few 100,000 light-years across. Finding one 16 million light-years wide shocked everyone. The discovery proved that current models of radio galaxy growth are incomplete. Yet Alcyoneus does not just sit peacefully in space. It feeds, it consumes, it grows by devouring everything around it. Galaxies are not isolated islands. They cluster together in groups bound by gravity, moving through space like schools of fish. The largest galaxies sit at cluster centers, and they grow by consuming their neighbors. This process happens constantly throughout the universe. Small galaxies wander too close to giants. Gravity pulls them in, and they get torn apart. Their stars scatter into the larger galaxy's halo. Astronomers call this galactic cannibalism, and both IC 1000, 101 and Alcyoneus practice it. IC 1000, 101 resides at the center of the Abell 2029 galaxy cluster, a massive collection containing thousands of galaxies bound together. The cluster spans roughly 15 million light-years across, and IC 1101 dominates its core. Smaller galaxies orbit around it like planets around a star. Over billions of years, some of those smaller galaxies drift inward. As they approach IC 1101, tidal forces stretch them. Stars on the side closest to IC 1101 feel stronger gravity than stars on the far side. This difference pulls the galaxy apart strand by strand. The process is not quick. A galaxy can survive dozens of passes through a cluster core before finally disrupting completely. Each pass strips away more stars, leaving them scattered in long tidal tails that stretch for hundreds of thousands of light-years. Eventually, nothing remains of the original galaxy except stars now orbiting within IC 1101's massive halo. The central black holes of consumed galaxies sink toward IC 1101's core, where they merge with the central supermassive black hole. This merger adds mass and might explain why IC 1101's black hole grew so large. Alcyoneus also feeds on neighbors. Its location in the cosmic web puts it along a filament of dark matter connecting galaxy clusters. These filaments act as highways, channeling smaller galaxies toward large structures. As galaxies flow along these dark matter streams, some encounter Alcyoneus. The giant's gravity captures them. Over millions of years, those captured galaxies lose energy through dynamical friction, a process where their motion through the cluster's gas and dark matter slows them down. They spiral inward and eventually merge with the central galaxy. Evidence of past mergers appears in IC 1101 structure. The galaxy's enormous diffuse core, formed through hundreds or thousands of smaller galaxies, colliding and merging over billions of years. Each merger heats the stellar population, causing stars to move faster and spreading the galaxy's mass over a larger volume. The result is a bloated, diffuse structure with a very low density compared to spiral galaxies. IC 1101 contains 100 trillion stars, but they are so spread out that vast regions of the galaxy remain nearly empty. The galactic halo extends 2 million light-years from the core, filled with ancient stars stripped from long-dead galaxies. These stars wander in the darkness between galaxy clusters, orphans from destroyed cosmic homes. They illuminate nothing. They warm nothing. They drift through the void as monuments to their galaxy's violent ends, and their color tells a story about time itself. When you observe IC 1101 through a telescope, you see a soft golden glow, no spiral arms, no dust lanes, No blue regions of star formation. Just a smooth, featureless ball of yellowish light that fades gradually into darkness. This appearance reveals the galaxy's age and its history. The color comes from the stars themselves, and those stars are ancient. Stars burn through nuclear fusion, converting hydrogen into helium in their cores. This process releases energy that we see as starlight. The temperature and composition of a star determine its color. Hot young stars burn blue-white. Middle-aged stars like ours appear yellow. Old stars glow red or orange. When you combine the light from trillions of stars, the overall color tells you the average age of the stellar population. IC 1101 appears golden yellow because most of its stars are old red and orange giants, mixed with middle-aged yellow stars. Very few young blue stars exist. Star formation nearly stopped billions of years ago when the galaxy exhausted its gas supply. The remaining stars have been aging ever since. As massive blue stars burned through their fuel and exploded, they left behind only longer-lived smaller stars. These cooler stars dominate the galaxy's light, giving it that characteristic golden appearance. The stars also contain high concentrations of metals. In astronomical terms, metals mean any element heavier than hydrogen and helium. These elements formed inside earlier generations of massive stars. When those stars exploded as supernovae, they scattered metals across space. New stars formed from this enriched gas, incorporating the metals into their composition. High metal content affects how stars age and what colors they produce. It also indicates the stars formed from heavily processed material, recycled multiple times through stellar life cycles. Elliptical galaxies like IC 1101 form through violent processes. Unlike spiral galaxies that grow gradually through steady gas accretion, ellipticals form primarily through mergers. When two spiral galaxies collide, their ordered rotation gets scrambled. The collision triggers intense star formation as gas clouds smash together. This starburst phase creates millions of massive blue stars in a relatively short time, but massive stars burn quickly. Within a few 100 million years, they all die, leaving behind the long-lived red and yellow stars we see today. The smooth appearance comes from random stellar orbits. In spiral galaxies, stars move in organized patterns around the galactic center, creating distinct structures like arms and bars. In elliptical galaxies, stellar orbits point in random directions. Some stars orbit clockwise, others counterclockwise. Some follow elliptical paths, others plunge through the core. This chaos produces a smooth distribution of light with no visible structure. The galaxy looks the same from every angle. Observing IC 1101 feels like looking at a ghost. The light reaching us left that galaxy over 1 billion years ago. We see it as it appeared in the deep past, glowing with the combined radiance of 100 trillion dying stars. Somewhere in that golden haze might be planets orbiting those ancient stars. Perhaps civilizations exist there, looking out at their night sky filled with ancient stellar light. But beneath that serene appearance lies something monstrous, something that defines the galaxy's very existence. In 2017, astronomers using Hubble Space Telescope data made a disturbing measurement. IC 1101's core, the central region where stellar density peaks, measures 13,700 light-years across. This makes it the largest galactic core ever observed. To understand how massive that is, remember that our entire galaxy spans 100,000 light-years. IC 1000. 101's core alone is larger than many dwarf galaxies. Galactic cores typically measure a few thousand light-years across at most. Large elliptical galaxies usually have cores around 3,000 to 5,000 light-years in diameter. Anything larger than 10,000 light-years is considered exceptionally unusual. IC 1101's core exceeds that threshold by 37%. The size defies standard formation models. Something strange happened during this galaxy's history to create such an enormous central region. Scientists have a theory, but it involves a catastrophic event so violent it strains belief. When two massive galaxies merge, their central supermassive black holes sink toward the new galaxy's center. For millions of years, they orbit each other, gradually spiraling closer through gravitational wave emission and dynamical friction. Eventually, they reach the final parsec, a distance of about 3 light-years, where merger becomes inevitable. The black holes collide and merge in a fraction of a second, releasing more energy than all the stars in the galaxy combined. This merger releases gravitational waves that kick stars out of the core. Imagine dropping a boulder into a pond. The initial splash sends water flying outward. Similarly, the black hole merger sends gravitational waves radiating through the galaxy's core, flinging stars away from the center. This process, called gravitational wave recoil, can empty out the galaxy's central regions. The ejected stars resettle in a larger, more diffuse distribution, creating an oversized core. IC 1101's huge core suggests its central black hole formed through many mergers, perhaps dozens or hundreds over billions of years. Each merger ejected stars, gradually hollowing out the center and puffing up the core to its current size. The stellar mass deficit, the amount of stellar matter missing from where it should be, measures approximately 490 billion times our star's mass. That missing matter got redistributed into the expanded core structure. The core is not empty. It still contains stars, but they are spread out over a much larger volume than expected. The stellar density is actually quite low compared to typical galactic cores. If you stood on a planet orbiting a star in IC 1101's core, you would see far fewer stars in your night sky than we see from Earth. The core's low density means the average distance between stars is much larger. Collisions between stars almost never happen, even though millions of stars crowd into the same region. Measuring the core accurately required incredibly detailed observations. Hubble captured images showing how starlight distributes across the galaxy's central regions. Astronomers fit mathematical models to these brightness profiles, determining where the core ends and the main galaxy body begins. The measurements were consistent across multiple wavelengths. The core truly reaches 13,700 light-years in radius. And at the very center of that vast core, the black hole waits, 70 billion times our star's mass, compressed into a region smaller than our solar system. The contrast is staggering, yet IC 1101's core is not the strangest thing about these cosmic monsters. Alcyoneus's true power reveals itself through the jets shooting from its black hole. These are not gentle streams of particles. They are cosmic fire hoses blasting matter across millions of light-years at 98% the speed of light. The energy required to accelerate material to such speeds exceeds anything we can replicate on Earth. The process begins deep in the black hole's gravitational well, where physics becomes extreme. Matter falling toward a black hole does not drop straight in. It spirals inward through an accretion disk, a swirling plate of superheated gas orbiting the black hole. Friction in the disk heats the material to millions of degrees. At these temperatures, atoms tear apart into individual electrons and atomic nuclei, creating a plasma. This plasma radiates intensely across all wavelengths, from radio waves to X-rays. The accretion disk glows brighter than trillions of stars combined. Not all the material reaches the event horizon. The black hole's rotation twists space-time around it, dragging magnetic field lines along. These field lines thread through the accretion disk, becoming incredibly twisted and amplified. Where the fields are strongest, they channel plasma away from the disk and accelerate it outward along the black hole's rotation axis. The process, called the Blandford-Znajek mechanism, extracts rotational energy from the black hole itself and converts it into jet power. The jets emerge perpendicular to the accretion disk, shooting in opposite directions like a cosmic double-sided blowtorch. They remain incredibly narrow near the black hole, sometimes only light years wide. But as they travel outward, they expand, eventually reaching widths of hundreds of thousands of light years. The jets maintain coherence over distances that boggle the mind. How does a stream of particles stay collimated across 8 million light years? Scientists are still working on complete answers. As the jets plow through the thin gas between galaxies, they push material aside, creating shock waves. These shock waves compress and heat the surrounding gas, causing it to glow in X-rays. The jets also carry magnetic fields that trap electrons and cosmic rays. These trapped particles spiral around the magnetic field lines, emitting synchrotron radiation visible in radio wavelengths. The radio emission traces the jet's path across space, revealing its full structure. Eventually, the jets slow down. The material they carry spreads out into massive lobes, the structures that make Alcyoneus 16 million light-years across. These lobes contain particles and magnetic fields, but very little actual mass. They exist as diffuse clouds of energy, gradually fading over millions of years as the trapped electrons lose energy. New material constantly flows in from the jets, keeping the lobes active and visible. The total kinetic energy in Alcyoneus's jets exceeds the energy output of all the stars in its host galaxy over the past billion years. The black hole alone, through its jets, dumps more energy into space than an entire galaxy full of nuclear fusion. This makes active galactic nuclei like Alcyoneus some of the most energetic phenomena in the universe, second only to the most powerful supernovae and gamma-ray bursts. But we are viewing all this from billions of years in the past. The light and radio waves we detect today left Alcyoneus 3 billion years ago. What does this galaxy look like right now? We cannot know. The light entering your telescope from Alcyoneus began its journey 3 billion years ago. Back then, Earth looked nothing like it does today. Multicellular life existed, but barely. The oceans hosted bacteria, algae, and simple organisms. Nothing lived on land except microbial mats. No plants, no animals, no insects. The atmosphere contained less oxygen than it does now. If you stood on that ancient Earth and looked up at the sky, you would suffocate within minutes. While that light traveled toward us, Earth transformed. The first plants colonized land around 500 million years ago. The first vertebrates crawled onto shore 400 million years ago. Dinosaurs rose and fell. Mammals evolved. Primates appeared. Humans developed civilization, invented writing, built cities, and created telescopes capable of detecting radio waves from cosmic sources billions of light years away. All of that happened during the time Alcyoneus's light crossed the void between us. Space itself expanded during those 3 billion years. The universe is not static. Galaxies move away from each other as space stretches. This expansion affects light traveling through it. As space expands, light waves stretch too, shifting toward redder wavelengths. Astronomers measure this redshift to determine how far away objects are. Alcyoneus has a redshift value of 0.25, meaning the wavelengths of its light increased by 25% during their journey. The radio waves we detect are not the same frequencies emitted. They stretched as they traveled, arriving at longer wavelengths than when they left. This time delay creates a fundamental problem. We cannot see Alcyoneus as it exists right now. We observe its past, frozen in ancient light. The galaxy might have changed dramatically since that light began traveling. It could have merged with neighbors, doubling in size. Its central black hole might have consumed so much material that the radio jets shut down. Perhaps another galaxy collided with it, triggering a burst of star formation that transformed its appearance. We have no way to know. The same applies to IC 1101. That galaxy sits 1.04 billion light-years away. The light we see left when Earth was in the Mesoproterozoic era, a time of simple life and barren continents. Over 1 billion years of potential change separates the IC 1101 we observe from whatever it looks like today. For all we know, IC 1101 merged with another supergiant galaxy and now appears even larger. Or perhaps it got disrupted by a close encounter with another massive structure. The possibilities remain endless. This disconnect between observation and reality frustrates astronomers. They want to study galaxies as they exist now, not as they appeared in the deep past. But the speed of light imposes an absolute limit. Information cannot travel faster than light. If Alcyoneus suddenly exploded today, we would not know for another 3 billion years. The universe enforces a cosmic speed limit, and distance creates a time delay we cannot overcome. Every distant object you observe through a telescope is a ghost, an afterimage, a recording of history. The farther you look, the further back in time you see. The most distant galaxies we observe appear as they existed over 13 billion years ago. Less than a billion years after the Big Bang, we watch their infant forms developing, knowing they are now ancient structures that might have changed beyond recognition or might not even exist anymore. This is the strange reality of astronomy. We study the past and call it the present. We measure ghosts and pretend they are real. But what truly disturbs astronomers is that nobody understands how these ghosts became so impossibly large. Alcyoneus should not exist. Neither should IC 1101. Current models of galaxy formation and evolution cannot fully explain structures this massive. Galaxies grow through two main processes. They accrete gas that forms new stars, and they merge with other galaxies. Both processes take time. The problem is that the universe is only 13.8 billion years old. That sounds like plenty of time, but building something 16 million light-years across requires an impossible sequence of events. Computer simulations of cosmic structure formation start with small density fluctuations in the early universe. Gravity amplifies these fluctuations, causing matter to clump together. Over hundreds of millions of years, the clumps grow into the first galaxies. These early galaxies are small, typically a few billion times our star's mass. They grow by colliding with neighbors, gradually building up to the massive structures we see today. The biggest galaxies assemble last, sitting at the intersections of cosmic web filaments, where material naturally flows. When astronomers run these simulations forward to the present day, they predict the existence of very large galaxies. The simulations successfully reproduce most observed galaxy properties, but they struggle with the absolute extremes. Galaxies as large as IC 1101 appear rarely in simulations, right at the edge of statistical probability. Alcyoneus barely appears at all. The simulations suggest that radio lobes extending 16 million light-years should not have had enough time to form. Radio jets require a feeding black hole. The black hole needs a steady supply of gas and stars to consume. This material comes from the surrounding galaxy and from gas flowing in along cosmic web filaments. But as jets pump energy into the surrounding space, they heat that gas. Hot gas resists falling into the galaxy. This creates negative feedback that limits how long jets can remain active. Most radio galaxies have short, active periods, perhaps a few tens of millions of years. Then the fuel supply runs out, the jets shut down, and the radio lobes fade. For Alcyoneus's lobes to reach 16 million light-years, the jets must have stayed active for hundreds of millions of years, possibly longer. Even traveling near the speed of light, material needs time to reach such distances, and the jets need to remain stable and powerful throughout that entire period. One interruption in the fuel supply would shut them down. When they reactivate later, they would create new jets that might point in different directions. Alcyoneus's lobes are perfectly aligned, suggesting continuous, uninterrupted jet activity. How did this galaxy maintain such a stable fuel supply for so long? Scientists proposed several theories. Perhaps Alcyoneus sits in an unusually low-density environment, where the thin gas creates less resistance to jet expansion. Maybe the galaxy lies along a cosmic web filament that funnels extra gas toward it, keeping the central black hole fed. The galaxy's orientation might play a role, with the jets happening to point along a particularly clear path through space. All of these factors might contribute, but none fully explain what we observe. The disturbing part is that Alcyoneus appears completely ordinary, except for its size. Its black hole is not exceptionally massive. Its stellar content is not unusual. Its radio power falls within normal ranges. There is no obvious special property that explains its giant size. If ordinary galaxies can sometimes grow this large, then our understanding of radio galaxy formation is incomplete. IC 1101 poses different questions. Its stellar mass approaches theoretical limits. The galaxy contains so much matter that it skirts the edge of what gravity can hold together. Add much more mass, and it might become gravitationally unstable. Yet both these monsters exist, defying expectations and mocking our models. Somewhere, out there, something even larger might be waiting. To truly grasp these scales, you need comparisons that mean something. Imagine standing in a football field. At one end zone, place a grain of sand. That grain represents our solar system, the bubble of space dominated by our star's gravity. Now place another grain of sand at the opposite end zone. The space between those two grains, 100 yards, represents the distance to the nearest star. 4 light years compresses to the length of a football field. Now imagine that entire football field shrunk down to the size of a period at the end of a sentence. That tiny dot represents the local stellar neighborhood around our star. Scale up again. Take 100,000 of those periods and arrange them in a spiral pattern. That spiral, spreading across roughly 3 feet of space, represents our Milky Way galaxy. 100 billion stars compressed into arm's length. Alcyoneus, by this scale, would stretch across almost 500 feet. You could not fit it inside most buildings. Try another comparison. If our star was the size of a grain of sand, our galaxy would span roughly the area of North America. All 100 billion stars packed into a space stretching from California to New York, from Canada to Mexico. IC 1101, at that same scale, would cover an area larger than the entire Earth's surface. You could scatter 50 galaxies the size of ours across IC 1101 and still have room left over. These comparisons still fail because space itself is mostly empty. Stars are so far apart that even in dense galactic cores, the distances between them dwarf the stars themselves. If you randomly appeared somewhere inside IC 1101, the odds overwhelmingly favor you materializing in empty space, far from any star. You might not see any stars nearby at all. The galaxy contains 100 trillion stars, but they are spread across such vast distances that most of the volume remains completely vacant. Light speed provides another useful comparison. Light travels from Earth to the Moon in about 1 second. It reaches Mars in roughly 3 minutes at closest approach. It takes light 8 minutes to travel from our star to Earth. Crossing our entire solar system, from our star to the edge of the Oort cloud, takes light about 1 year. That defines 1 light year. Our galaxy spans 100,000 light years. Alcyoneus stretches 16 million light years. A photon traveling across Alcyoneus would need 160,000 complete trips across our entire galaxy. Human minds did not evolve to comprehend these scales. Our brains developed to track threats in our immediate environment, estimate distances to nearby objects, and understand spatial relationships in human-scale terms. We can imagine a room, a building, a city, maybe even the curvature of Earth, but 16 million light years? The numbers mean nothing emotionally. You can calculate them, you can write them down, but you cannot feel them. The scales transcend human intuition. This is why astronomy can feel so alienating. We study structures so large that they reduce everything familiar to insignificance. Our entire planet, every person who ever lived, all of human history, compresses to a speck too small to see. And that speck orbits an ordinary star in an ordinary galaxy that would be utterly invisible next to Alcyoneus, or IC 1101. We are not even rounding errors in cosmic arithmetic. We are far, far smaller than that. Yet, despite our cosmic insignificance, we figured out how to detect these giants. We built telescopes, developed mathematics, constructed theories, and pointed our instruments at distant points of light. Against all odds, tiny beings on a tiny world measured the largest structures in existence. And those measurements revealed something even more disturbing about the nature of space itself. Galaxies do not scatter randomly through space. They organize into a vast network called the cosmic web, a structure so large it encompasses the observable universe. This web formed from tiny density fluctuations in the early universe that gravity amplified over billions of years. Matter flowed along these density patterns, creating filaments, walls, and voids. The cosmic web resembles neural networks in human brains or mycelia networks underground, a branching structure connecting everything. The filaments contain dark matter, the mysterious substance that makes up 85% of all matter but emits no light. Dark matter only interacts through gravity. We detect it by observing how visible matter moves in response to gravitational fields we cannot see. The filaments act as gravitational highways, channeling normal matter along specific paths. Galaxies form where filaments intersect, clustering together at cosmic crossroads. The largest galaxy clusters sit at the busiest intersections, where multiple filaments converge. Alcyoneus likely sits near one of these filaments. Its location in the cosmic web might explain its enormous size. As gas flows along the filament toward the galaxy, it provides a steady supply of fuel for the central black hole. This fuel keeps the jets active for hundreds of millions of years, allowing them to inflate the giant radio lobes. Without this cosmic supply line, the black hole would have exhausted local gas supplies long ago and shut down. The filament connects Alcyoneus to distant reservoirs of matter, keeping it fed and growing. IC 1101 occupies a similar position at the center of the Abell 2029 galaxy cluster. The cluster itself sits at a major cosmic web node, where several filaments meet. Over billions of years, galaxies flowed along these filaments toward the cluster core. As they arrived, IC 1101's gravity captured them. Some merged with the central giant, adding their stars and gas to its mass. Others orbit in the cluster, gradually losing energy and spiraling inward. The process continues today, ensuring IC 1101 keeps growing, even as its internal star formation shuts down. The cosmic web also creates vast voids, regions nearly devoid of galaxies. These voids stretch for hundreds of millions of light-years, containing very little visible matter. The largest void, the Boötes void, spans 330 million light-years. If you stood in the center of that void, you might not see any galaxies at all in any direction. The nearest structures would lie beyond the reach of even powerful telescopes. These voids form naturally as matter flows away from underdense regions toward overdense filaments and clusters. Scientists study the cosmic web using massive surveys that map galaxy positions across the sky. By analyzing how galaxies cluster together, they reconstruct the underlying dark matter distribution. Computer simulations reproduce the cosmic web structure by starting with the conditions present shortly after the Big Bang and evolving forward in time. The simulations match observations remarkably well, confirming that gravity sculpted the universe into this web pattern over billions of years. But the cosmic web is not static. It continues evolving. Filaments stretch as the universe expands. Clusters grow more massive as they accumulate additional galaxies. Voids expand as matter drains away from them. In the far future, After hundreds of billions of years, the universe will become even more structured. Galaxy clusters will merge into massive superclusters. Regions between these superclusters will become emptier. Eventually, accelerating expansion driven by dark energy will tear even these structures apart. But that fate lies in the incomprehensibly distant future. For now, the cosmic web shapes where the largest galaxies form and determines their ultimate size. Alcyoneus and IC 1101 both benefited from prime real estate in this vast structure. But something happened to these galaxies that ensures they will never create new stars again. IC 1101 is dying. Star formation, the process that once created trillions of stars within it, has nearly ceased. The galaxy exhausted most of its cold gas billions of years ago. What remains is a population of aging stars slowly burning through their remaining fuel. Astronomers classify galaxies like this as red and dead, indicating their stellar populations skew old and no significant star birth occurs. Understanding how galaxies become red and dead reveals fundamental processes shaping cosmic evolution. Star formation requires specific conditions. You need cold molecular gas, primarily hydrogen, compressed into dense clouds. These clouds must cool below about 10,000 degrees Kelvin, allowing gravity to overcome thermal pressure. Once sufficiently compressed, the cloud fragments into smaller clumps. Each clump continues collapsing until its core becomes hot enough to ignite nuclear fusion. A star is born. The process converts gas into stars, gradually depleting the galaxy's fuel supply. Young spiral galaxies, like our Milky Way, still have abundant cold gas. Our galaxy converts approximately 2 to 3 times our star's mass of gas into new stars every year. This might sound like a lot, but with roughly 10 billion times our star's mass of gas available, the Milky Way can continue forming stars for billions of years. The process maintains the galaxy's spiral structure and creates regions of active star formation visible as bright blue areas in photographs. IC 1101 stopped forming stars at significant rates billions of years ago. Several factors contributed to this shutdown. First, the galaxy merged repeatedly with other galaxies. Each merger triggered intense starbursts as colliding gas clouds compressed and collapsed. These bursts created massive stars that burned through their fuel in mere millions of years. The supernovae explosions from dying massive stars heated surrounding gas, making it harder for new stars to form. Multiple rounds of mergers and starbursts gradually exhausted the cold gas supply. Second, the central black hole played a role. As it fed on infalling material, it generated powerful jets that heated gas throughout the galaxy. This process, called AGN feedback, prevents cooled gas from settling into the galactic disk, where it could form stars. The black hole essentially regulates star formation, preventing the galaxy from converting all its gas into stars too quickly. But it also means that once most of the gas is gone, very little remains to form new generations of stars. Third, IC 1101's location in a galaxy cluster matters. The space between cluster galaxies contains hot gas, a diffuse plasma heated to tens of millions of degrees by gravitational compression and past merger activity. When IC 1101 moves through this hot medium, a process called ram pressure stripping can blow away its remaining cold gas. The galaxy's motion through the cluster creates a wind that strips away loosely bound material, removing the raw ingredients needed for star formation. The result is a galaxy full of old stars slowly dying. The most massive stars, which burn blue-white and live only a few million years, died billions of years ago. What remains are smaller, longer-lived stars that glow red, orange, and yellow. These stars will continue burning for many billions of years, but no new blue stars replace the ones that die. Over time, the galaxy grows redder and dimmer as its stellar population ages. Eventually, in the far future, only the smallest red dwarf stars will remain, faintly glowing in an increasingly empty galaxy. Alcyoneus faces a similar fate. Its star formation shut down long ago. The galaxy exists as a fading ember, its stellar population gradually dimming over cosmic time. No new stars mean no new planets, no new solar systems, no new chances for life to arise. Whatever civilizations might exist in these galaxies, inherited stars formed billions of years ago. When those stars die, no replacements will come. This is the life cycle of giant elliptical galaxies. They form through violent mergers, experience intense bursts of star creation, then slowly fade into obscurity. But there is one way these dead galaxies can return to life. Galaxies collide constantly throughout the universe. Despite the vast distances between them, gravity ensures that over billions of years, neighbors eventually encounter each other. These collisions rank among the most spectacular events in the cosmos, reshaping galaxies and triggering enormous bursts of star formation. IC 1101 and Alcyoneus both formed through countless such collisions, their current massive sizes the result of accumulated mergers over cosmic history. A typical galaxy collision unfolds over hundreds of millions of years. The galaxies approach each other, accelerating as gravity pulls them together. On first pass, they might simply swing around each other, distorting each other's shapes through tidal forces. Long streams of stars get pulled out, creating tidal tails that stretch for hundreds of thousands of light years. These tails often form bridges between the two galaxies, visible in deep telescope images as faint ribbons of light. As the galaxies separate after the first pass, their mutual gravity drains orbital energy. They slow down, fall back together, and collide again. This process repeats multiple times, each collision becoming more violent as the galaxies lose energy and approach more closely. Eventually, they merge completely, their stars mixing into a single larger galaxy. The entire process, from first encounter to final merger, can take over 1 billion years. The collision does not involve stars physically hitting each other. The spaces between stars are so vast that stellar collisions almost never occur. Instead, gravity reshapes the galaxies. Ordered motion gets scrambled. Spiral galaxies, with their organized rotating disks, transform into elliptical galaxies with random stellar orbits. The transformation is permanent. Once a spiral galaxy merges with another large galaxy, the spiral structure cannot reform. But the gas clouds within galaxies do collide. Unlike stars, gas occupies a more continuous distribution and interacts through electromagnetic forces. When gas clouds smash together at speeds of hundreds of miles per second, they compress and heat. Some regions compress enough to trigger runaway gravitational collapse. Stars form by the millions in these compressed zones, creating brilliant starburst regions visible across the electromagnetic spectrum. Our galaxy is currently colliding with a smaller neighbor, the Sagittarius Dwarf Elliptical Galaxy. This small galaxy is being torn apart by our galaxy's tidal forces. Long streams of stars from it wrap around our galaxy multiple times, evidence of several previous passes. In approximately 4 to 5 billion years, our galaxy will collide with the Andromeda Galaxy. That collision will scramble both galaxies, triggering massive star formation and eventually merging them into a giant elliptical galaxy. Astronomers have already named this future galaxy Milky Way. IC 1101 formed through dozens or hundreds of major mergers. Each merger added mass, stars, and gas. The accumulated effect produced the supergiant structure we observe today. Evidence of its merger history appears in its stellar populations. Deep spectroscopic studies reveal stars with different ages and chemical compositions mixed throughout the galaxy. These stars came from different progenitor galaxies that merged at different times, each contributing its stellar population to the growing giant. Alcyoneus likely has a similar history. Its host galaxy grew through mergers until it accumulated enough mass to host a supermassive black hole capable of generating the enormous jets we observe. Without the mass added by multiple mergers, the black hole might never have grown large enough to power radio lobes stretching 16 million light-years. But there is a limit to how large galaxies can grow. Dark energy ensures that the universe is accelerating. Space itself expands faster now than it did in the past, driven by dark energy, a mysterious force that pushes everything apart. This acceleration imposes a fundamental limit on how large structures can grow. Any region where gravity successfully pulls matter together can continue growing, but only until expansion tears it away from nearby material. Beyond a certain scale, expansion wins and structure formation stops. Dark energy was discovered in 1998 when astronomers measured distances to distant supernovae. They expected to find that the universe's expansion was slowing down, decelerated by gravity. Instead, they found expansion accelerating. Distant supernovae appeared dimmer than predicted, meaning they were farther away than expected for their redshift. Something pushed them away faster than models predicted. That something, for lack of a better term, became known as dark energy. Dark energy behaves unlike anything familiar. It does not clump or cluster. It fills space uniformly, exerting a repulsive gravitational effect that increases with distance. The farther apart two objects are, the stronger dark energy pushes them apart. This repulsion remained weak in the early universe when everything was closer together. But as the universe expanded, dark energy's influence grew. Roughly 5 billion years ago, dark energy became the dominant force controlling cosmic expansion. The accelerating expansion affects galaxy formation. In regions where matter is gravitationally bound, like galaxy clusters, expansion cannot pull structures apart. Gravity holds them together. But on larger scales, where gravitational binding is weaker, expansion wins. Material beyond a certain distance gets carried away by expanding space, moving faster and faster, eventually disappearing beyond the cosmic horizon, where space recedes faster than light can travel. This creates a cosmic horizon limit for structure sizes. Any galaxy trying to accrete material from distances beyond several tens of millions of light-years faces expansion, pulling that material away faster than gravity can pull it in. The material becomes cosmologically inaccessible. This is why Alcyoneus's 16 million light-year size represents such an extreme. It approaches the maximum practical size for any structure in an accelerating universe. Anything significantly larger would require pulling in material from regions where expansion dominates. IC 1000, 100, and 1's mass also approaches theoretical limits. A galaxy cannot grow arbitrarily massive without becoming unstable. At some point, the outer regions become so weakly bound that tidal forces from neighboring structures can strip them away. Very massive galaxies also exhaust their fuel supplies faster as their strong gravity heats infalling gas, making it harder for that gas to cool and form stars. There is a natural limit to galaxy mass determined by the balance between accretion and feedback processes. Computer simulations suggest the largest galaxies in today's universe are probably near the maximum sizes they can achieve. Future growth will be limited. IC 1000, 100, and 1 might continue absorbing small galaxies from its cluster, but major mergers with other supergiant galaxies become increasingly unlikely as expansion pulls potential merger partners farther apart. Alcyoneus's jets might fade as its black hole exhausts local gas supplies. The accelerating expansion ensures that new material cannot flow in from large distances. In the far future, hundreds of billions of years from now, dark energy will dominate completely. Galaxy clusters will remain bound, but everything outside them will recede beyond reach. Galaxies will become isolated islands in an ever-expanding void. No new mergers will occur. No new growth will happen. The largest galaxies will simply age, their stars slowly dying, until only the faintest red dwarf stars remain, glowing weakly in otherwise dead galaxies. The universe has already created its largest structures. We live in the era where giants like Alcyoneus and IC 1101 exist at their maximum size. But the mass contained in IC 1101 dwarfs even your wildest guesses. IC 1101 weighs approximately 1 quadrillion times the mass of our star. That number is one followed by 15 zeros, 1,000 trillion, a million billion. The number is so large that writing it out fully becomes meaningless. To understand this mass, you need context that makes the scale tangible. Our star contains enough matter to make 330,000 Earths. IC 1101 contains enough matter to make 330,000 trillion Earths. The galaxy could swallow our entire solar system 1 quadrillion times and still have room for more. Where did all this mass come from? Most of it is not actually stars. About 85% of the galaxy's mass consists of dark matter, the invisible substance that interacts only through gravity. Dark matter formed the gravitational scaffolding that allowed visible matter to accumulate. Without dark matter, galaxies could not have formed at all. The ordinary matter, the stuff that makes up stars, planets, and everything we can see, represents only 15% of the total mass. Even that 15% staggers the imagination. IC 1101 contains roughly 100 trillion stars, each averaging about half our star's mass. That alone accounts for 50 trillion times our star's mass in stellar material. Add the gas, dust, and stellar remnants like white dwarfs, neutron stars, and stellar mass black holes, and the visible matter totals around 150 trillion times our star's mass. Multiply that by about 6.7 to include the dark matter, and you reach approximately 1 quadrillion total mass. The dark matter forms an enormous halo surrounding the visible galaxy. This halo extends far beyond the visible stars, reaching hundreds of thousands of light years into space. Most of the galaxy's volume contains only dark matter, with occasional stars wandering through. If you could somehow see dark matter, IC 1101 would appear much larger and more diffuse than it does in optical images. The golden glow of stars represents only the visible tip of a much more massive structure. Measuring a galaxy's mass requires indirect techniques. Astronomers cannot count every star and weigh them individually. Instead, they observe how fast stars and gas move as they orbit the galactic center. The orbital velocity depends on the total mass pulling on them gravitationally. By measuring velocities at different distances from the center, astronomers reconstruct the mass distribution. The measurements consistently show that most mass is invisible, revealing the dark matter halo's presence. The supermassive black hole at IC 1101's center contributes negligible mass compared to the galaxy's total. Even at 70 billion times our star's mass, the black hole represents only 0.007% of the galaxy's total mass. It is massive by black hole standards, but tiny compared to the galaxy itself. The black hole's gravitational influence dominates only the innermost few thousand light years. Beyond that, the collective gravity of billions of stars and the dark matter halo control the motion of material. This quadrillion times our star mass creates intense gravitational effects. Smaller galaxies passing near IC 1101 get torn apart by tidal forces. Stars get stripped from them, scattered into long tails. The remnants eventually merge with IC 1101, adding their mass to the giant. This gravitational cannibalism explains how IC 1101 grew so massive over billions of years. It sits at the bottom of a deep gravitational well, capturing everything that wanders too close. But not all of IC 1101's mass concentrates in its bright central core. Much of it spreads across a vast halo that becomes increasingly difficult to detect. Beyond IC 1101's bright core lies a vast halo of faint starlight. This halo extends approximately 2 million light-years from the galactic center, making it wider than the distance between our galaxy and Andromeda. The halo contains billions of stars, but they are spread so thinly that the region appears nearly empty. Stand on a planet orbiting a halo star, and your night sky would be almost completely black. The nearest neighboring star might be hundreds of light-years away. These halo stars are orphans. They once belonged to smaller galaxies that IC 1101 destroyed through tidal interactions. As those smaller galaxies approached IC 1101, gravitational forces pulled stars away from them. The stars could not escape IC 1101's deep gravitational well, but they also could not settle into stable orbits in the main galaxy. Instead, they scattered throughout the halo, following chaotic paths that carry them far from the galactic center before returning inward. The halo's faint light makes it incredibly difficult to study. The stars are so spread out that they contribute very little brightness. Detecting them requires extremely long exposures with sensitive instruments, filtering out light from foreground stars and background galaxies. Even then, the halo appears as a subtle glow, barely distinguishable from the sky background. Most images of IC 1101 show only the bright central regions, cutting off where the surface brightness drops too low. Recent studies using deep imaging from Hubble and other telescopes revealed that IC 1101's halo contains roughly 10 trillion stars. That is 1/10 of the galaxy's total stellar population. These stars are old, primarily red giants and dim main sequence stars. Their average age exceeds 10 billion years. They formed in smaller galaxies that merged with IC 1101 between 5 and 10 billion years ago. Chemical analysis of halo stars reveals lower metal content than core stars, confirming they came from less massive progenitor galaxies that had not enriched their gas with as many heavy elements. The halo also contains globular clusters, dense balls of ancient stars that orbit the galaxy in elongated paths. IC 1101 hosts thousands of globular clusters, far more than our galaxy's roughly 150. Each cluster contains between 100,000 and 1 million stars packed into a region only a few dozen light-years across. The clusters survive as bound units even as they orbit through the galaxy's gravitational field. Their high densities prevent tidal forces from tearing them apart. Astronomers debate where the halo truly ends. At what point does the galaxy's influence stop and intergalactic space begin? There is no clear boundary. The stellar density gradually decreases with distance, fading into the intracluster light, a diffuse glow filling the space between galaxies in the cluster. Some of those stars might technically belong to IC 1101's halo. Others might be truly intergalactic, stripped from multiple galaxies and now wandering freely through the cluster. The halo's size poses interesting questions about galactic identity. If a star orbits 2 million light-years from the galactic center, is it really part of that galaxy? It responds to the galaxy's gravitational field. Its orbit depends on the galaxy's mass, yet it lives in isolation, never interacting with other stars, never experiencing the galactic environment most stars inhabit. These halo stars exist in a strange liminal space, technically part of a galaxy but functionally isolated in near-empty space. And the light from these halo stars tells a story written in color. Color reveals age. When you observe IC 1101 through a telescope, the galaxy glows with a soft yellow-gold hue. This color is not arbitrary. It directly reflects the ages and compositions of the stars producing the light. Young galaxies burn blue-white, energized by massive young stars. Middle-aged galaxies appear yellowish. Old galaxies glow red-orange. IC 1101's golden yellow color marks it as an aging structure, its stellar population dominated by middle-aged and old stars with very few young ones. The color comes from stars similar to our own but older. Our star is about 4.6 billion years old and appears yellow. Stars in IC 1101 average over 7 billion years old, and many exceed 10 billion years. These stars burn cooler than young blue stars, emitting more light in yellow, orange, and red wavelengths. When you combine the light from 100 trillion of these stars, the result is the golden glow that characterizes IC 1101. The stars also contain high metal content. In astronomical terminology, metals mean any element heavier than hydrogen and helium. The universe began with only hydrogen, helium, and traces of lithium. All heavier elements formed inside stars through nuclear fusion. When massive stars exploded as supernovae, they scattered these newly formed elements across space. Subsequent generations of stars incorporated these metals into their composition. The more metals a star contains, the more generations of previous stars contributed to the gas from which it formed. IC 1101 stars show metal abundances 2 to 3 times higher than our star. This indicates they formed from gas enriched by many previous stellar generations. The high metal content affects stellar properties. Metal-rich stars have higher opacity, meaning their outer layers block photons more effectively. This increases the star's size and changes its temperature. For a given mass, a metal-rich star burns slightly cooler and appears redder than a metal-poor star. This contributes to IC 1101's overall yellow-gold color. Spectroscopy allows astronomers to measure stellar composition. By spreading a star's light into a spectrum, they identify absorption lines created by different elements. Each element absorbs light at specific wavelengths, creating a unique fingerprint. Iron creates particularly strong lines, making it easy to measure. The strength of these lines indicates how much iron and other metals the star contains. Observations of IC 1101 show strong metal absorption lines across its spectrum, confirming high metal abundances. The galaxy's color will continue reddening over billions of years. As more stars age and the remaining massive stars die, the average stellar mass decreases. Smaller stars burn cooler and redder. Eventually, in the far future, IC 1101 will glow deep red-orange, then fade to a dim red as only the smallest, coolest stars remain. This is the inevitable fate of all galaxies that stop forming new stars. They redden, dim, and slowly fade from view. But understanding IC 1101's color required technology that can see what human eyes cannot. Radio observations revealed Alcyoneus. When visible light showed nothing unusual, human eyes detect only a tiny fraction of the electromagnetic spectrum. We see wavelengths between roughly 400 and 700 nanometers, the range we call visible light. But electromagnetic radiation exists across a vast range of wavelengths, from gamma rays shorter than atoms to radio waves longer than buildings. Each wavelength reveals different phenomena. To see Alcyoneus's true size, you need to look in radio wavelengths completely invisible to human vision. Radio waves have wavelengths ranging from about 1 millimeter to 100 kilometers. Radio telescopes detect these waves using large metal dishes that focus the signals onto receivers. The wavelengths are so long that dish surfaces do not need to be perfectly smooth. Unlike optical telescopes that require mirror surfaces polished to nanometer precision, radio dishes can use metal, mesh, or even chicken wire and still function effectively. This makes building very large radio telescopes practical. The low-frequency array that discovered Alcyoneus operates at wavelengths between 1.7 and 3.4 meters. These long wavelengths penetrate through dust and gas that blocks visible light. They reveal structures powered by magnetic fields and relativistic particles, phenomena that emit little or no visible light. Alcyoneus's radio lobes glow brightly at these wavelengths, but remain completely invisible to optical telescopes. The radio emission comes from synchrotron radiation, light produced by electrons spiraling around magnetic field lines at nearly the speed of light. As these electrons move through magnetic fields, they curve, and this acceleration causes them to emit photons. The exact wavelength of emitted light depends on the electron energy and the magnetic field strength. For the conditions in Alcyoneus's lobes, synchrotron radiation peaks in radio wavelengths. The lobes contain relatively little actual mass. Most of the volume is nearly empty space, with only trace amounts of plasma and magnetic fields. The plasma density is far lower than the best vacuum we can create on Earth. Yet these diffuse structures shine brightly in radio observations because the electrons have tremendous energy. A small number of highly energetic particles produces strong radio emission. Radio astronomy revolutionized our understanding of the universe. Before radio telescopes, astronomers only saw the visible universe, missing entire classes of objects. Radio observations discovered pulsars, quasars, and mapped the cosmic microwave background radiation left over from the Big Bang. They revealed the structure of our galaxy's spiral arms hidden behind dust. They found thousands of radio galaxies like Alcyoneus. Without radio astronomy, we would know far less about cosmic structure and evolution. Modern radio telescopes combine signals from multiple dishes spread across large distances. This interferometry technique creates a virtual telescope with an aperture as large as the separation between dishes. The low-frequency array spans much of Europe, giving it effective resolution far better than any single dish could achieve. This allowed astronomers to map Alcyoneus's lobes in detail, despite their enormous size and faint emission. Future radio telescopes promise even better sensitivity. The square-kilometre array, currently under construction in South Africa and Australia, will dwarf existing facilities. It might discover radio galaxies even larger than Alcyoneus, structures that current telescopes are too insensitive to detect. The universe likely contains phenomena we cannot yet see, waiting for sufficiently powerful instruments, but Alcyoneus's extreme size is not random. Its location in space matters tremendously. Galaxies do not exist in isolation. They cluster together in groups bound by gravity. Small groups contain dozens of galaxies. Large clusters contain thousands. The richest clusters dominate cosmic structure, sitting at intersections of cosmic web filaments where matter naturally accumulates. IC 1101 and Alcyoneus both reside in environments that directly influence their growth. Their sizes result not just from internal properties, but from where they sit in the cosmic web. IC 1101 anchors the center of Abell 2029, a massive galaxy cluster containing over 2,000 galaxies. The cluster's total mass exceeds 1 quadrillion times our star's mass, most of it in dark matter. Hot X-ray emitting gas fills the space between galaxies, heated to tens of millions of degrees by gravitational compression. This hot gas contains more mass than all the cluster's stars combined. Its presence affects how galaxies evolve within the cluster. Galaxies moving through cluster cores experience ram pressure stripping. Their motion through the hot intracluster gas creates a wind that blows away their own gas. Like a paper bag thrown from a moving car, the galaxy's gas gets stripped away by pressure from the surrounding medium. This process removes the raw material needed for star formation, gradually shutting down the galaxy's ability to make new stars. IC 1101 likely experienced this process, accelerating its transformation into a dead galaxy. Being at the cluster center provides advantages. Central galaxies grow through cannibalism more effectively than others. They sit at the bottom of the cluster's gravitational well, where smaller galaxies naturally sink over time. Dynamical friction, a drag force caused by gravitational interactions with thousands of other galaxies, removes energy from infalling galaxies. They slow down, sink toward the center, and eventually merge with the central giant. This process feeds IC 1101, allowing it to grow larger than any other galaxy in its cluster. Alcyoneus benefits from its location along a cosmic web filament. These filaments act as highways, channeling gas from voids toward denser regions. The steady flow of material along the filament keeps Alcyoneus's central black hole fed. Without this cosmic fuel supply, the black hole would have exhausted local gas long ago. The jets would have shut down, and the radio lobes would have faded. Alcyoneus's extreme size required both a massive black hole and a location that provides continuous fuel delivery over hundreds of millions of years. Environment also determines galaxy morphology. Galaxies in dense clusters experience more mergers and tidal interactions than isolated galaxies. This drives the transformation from spiral to elliptical forms. Our Milky Way and Andromeda exist in a relatively sparse environment with only a few dozen neighboring galaxies. They maintained their spiral structures for over 10 billion years. IC 1101 formed in a rich cluster where mergers happened frequently. It became an elliptical giant, its spiral structure destroyed by repeated violent interactions. Statistical studies confirm environment's importance. The most massive galaxies almost always sit at cluster centers. Very few supergiant galaxies exist in isolation. Those that do likely formed in clusters that later dispersed due to unusual dynamics. The strong correlation between galaxy mass and environment proves that location matters. Where you are determines what you become. Understanding this helps astronomers predict where to find the next record-breaking galaxy. They should look at the centers of the most massive clusters, at the densest nodes in the cosmic web. That is where the universe concentrates matter most effectively. That is where the largest structures grow. But even in these preferred locations, galaxies leak stars into the darkness between them. The space between galaxies in clusters is not completely dark. A faint glow called intracluster light fills these voids, produced by stars that no longer belong to any specific galaxy. These orphaned stars wander freely through the cluster, stripped from their parent galaxies by tidal forces during close encounters. The intracluster light represents a graveyard of destroyed galaxies, their stellar populations scattered across millions of light years. When two galaxies pass close to each other in a cluster, tidal forces stretch them. Stars on the side nearest the other galaxy feel stronger gravity than stars on the far side. This differential pull creates tides that stretch the galaxy into an elongated shape. If the encounter is close enough and fast enough, some stars gain enough energy to escape the galaxy entirely. They enter the cluster's gravitational field, now bound to the cluster as a whole rather than any individual galaxy. Over billions of years, repeated tidal interactions strip stars from many galaxies. The accumulated orphan stars create a diffused background glow throughout the cluster. This intracluster light is extremely faint, typically only about 1% as bright as the sky background. Detecting it requires very careful observations that subtract all foreground and background sources. Only then does the faint glow of wandering stars become visible. Observations of Abell 2029 reveal significant intracluster light around IC 1101. Studies estimate that roughly 10 to 20% of the cluster's total starlight comes from intracluster stars rather than stars in galaxies. This represents trillions of orphaned stars wandering between galaxies. Many probably came from IC 1101 itself during mergers with other large galaxies. Close encounters during mergers eject stars into the surrounding cluster. These intracluster stars follow complex orbits through the cluster's gravitational field. Some travel on nearly circular paths around the cluster center. Others follow highly elongated orbits that carry them from the dense core out to the cluster's edge and back. A few might eventually fall back into IC 1101 or other large galaxies, completing their journey home. But most will wander forever, orphans in the cosmic void. Life on planets orbiting intracluster stars would be strange. The night sky would be nearly black, with no nearby stars visible. Only the faint glow of distant galaxies would break the darkness. The galaxy that once was home would appear as a faint fuzzy patch, one among thousands. There would be no galactic plane, no Milky Way band of light arcing across the sky. Just darkness and distant island universes. Any civilization arising on such a world would struggle to develop astronomy without nearby stars to study. The intracluster light tells us about the violent history of galaxy clusters. It records all the close encounters, mergers, and tidal stripping events that occurred over billions of years. By measuring how much intracluster light exists and where it is distributed, astronomers reconstruct the cluster's assembly history. More intracluster light indicates more violent interactions. Less suggests a quieter evolution with fewer disruptions. Future deep surveys will map intracluster light in thousands of clusters, revealing patterns in how galaxies evolve in different environments. This will improve models of galaxy formation and help predict what structures might exist in the distant universe we cannot yet observe. But measuring these faint glows requires astronomers to solve difficult technical problems about where galaxies truly end. How do you measure something that has no clear edge? Galaxies gradually fade as you move away from their centers. At some point, the starlight becomes so faint it blends into the background sky. Where you choose to define the galaxy's boundary determines its measured size. Different astronomers using different techniques get different answers. This makes comparing galaxy sizes surprisingly difficult and controversial. Optical measurements typically use surface brightness limits. Astronomers define the galaxy's edge as the radius where surface brightness drops below a specific threshold, usually 25 magnitudes per square arcsecond in visible light. This corresponds to roughly 1/10,000,000th the brightness of the night sky between stars. At this limit, the galaxy's light becomes too faint to distinguish from background sources. By this metric, IC 1101 measures approximately 6 million light-years across. But that measurement misses the galaxy's faint outer halo. Deeper observations with longer exposures reveal stars extending much farther. Some studies trace IC 1101's halo out to 8 million light-years or more. Which measurement is correct? Both are, in a sense. They simply define the galaxy's size differently. It is like asking how large a city is. Do you measure the dense urban core, the suburbs, the entire metropolitan area? Each gives a valid but different answer. Radio measurements of Alcyoneus face similar challenges. The radio lobes fade gradually at their edges. Deciding where they end requires choosing an intensity cutoff. Different cutoffs give different sizes. The 16 million light-year measurement represents the distance between the outermost detectable radio emission on opposite sides. But fainter emission might extend farther, below current detection limits. Future, more sensitive observations might reveal the lobes are even larger. Mass measurements provide another way to define galaxy size. The virial radius marks the distance where the galaxy's gravitational influence transitions to being dominated by the surrounding cluster or cosmic web. Material inside the virial radius is gravitationally bound to the galaxy. Material outside is not. By this definition, IC 1101 extends several million light-years, including vast amounts of dark matter, invisible in optical images. The problem extends beyond individual galaxies. When does a galaxy cluster end? Where does it transition to the cosmic web filaments connecting clusters? These boundaries remain fuzzy and contested. Astronomers must make somewhat arbitrary choices about where to draw lines in naturally continuous distributions. Despite these challenges, the measurements are not meaningless. They provide consistent comparisons, as long as everyone uses the same methodology. Saying IC 1101 is larger than our galaxy remains true regardless of exactly where you define the boundary. The ratio stays roughly constant. Alcyoneus is genuinely larger than other radio galaxies by any reasonable measurement standard. The 16 million light-year figure might be approximate, but it accurately represents that this galaxy exceeds all others. Improving measurements requires better instruments. Deeper observations reveal fainter structures. Higher resolution shows more detail. Future telescopes will refine our understanding of where these giant galaxies truly end, but some uncertainty will always remain. Nature rarely provides clean boundaries. Reality exists in shades of grey, not sharp lines. And within these massive structures, with fuzzy boundaries, lie possibilities that stagger the imagination. IC 1101 contains 100 trillion stars. Conservative estimates suggest most stars host at least one planet. That means IC 1101 likely contains 100 trillion planets or more. Even if only 1 in a million planets could support life, that still leaves 100 billion potentially habitable worlds. The galaxy might host more life-bearing planets than there are humans who have ever lived on Earth. The implications are staggering. Consider the time available. IC 1101 stars are over 7 billion years old. Life on Earth arose about 3.7 billion years ago. Civilizations on planets orbiting IC 1101 stars could have had 7 billion years to develop. For context, humans evolved into recognizable form only 300,000 years ago. Written history spans barely 5,000 years. What could a civilization accomplish with 7 billion years? The question transcends human comprehension. Such civilizations might have spread across their galaxy if they achieved interstellar travel and expanded outward at even 1% the speed of light. They could colonize the entire galaxy in less than 100 million years. With billions of years available, hundreds of different civilizations might have arisen, spread, encountered each other, and built galactic-scale structures. IC 1101 could host civilizations we would perceive as gods, their technology so advanced it appears magical. Or perhaps intelligence is extraordinarily rare. Maybe IC 1101 contains trillions of barren worlds, where life never arose, or arose but never developed complexity, or developed complexity but never achieved intelligence. We have exactly one data point, Earth. We do not know if life is common or rare. We do not know if intelligence is inevitable or nearly impossible. IC 1101 could be filled with life or completely dead. The galaxy's age creates another challenge for life. Most of IC 1101 stars formed billions of years ago. They are aging. The most massive ones already died, exploding as supernovae. The remaining stars will continue burning for billions more years, but eventually they too will die. No new stars form to replace them. Any civilization in IC 1101 must deal with the reality that their star is dying and no younger stars exist nearby. They could potentially migrate between stars, moving to younger systems as old ones fade. With billions of stars available, even a galaxy that stopped forming new stars billions of years ago still offers immense opportunities. But this requires technology far beyond our current capabilities. We can barely launch probes to the edge of our solar system. Interstellar travel remains theoretical. Yet, with billions of years, such challenges might become trivial. Communication across IC 1101 poses interesting problems. The galaxy spans millions of light years. A message sent from one side takes millions of years to reach the other. By the time you receive a reply, millions of years have passed. Civilizations would rise and fall during the communication delay. This makes real-time conversation impossible. Any interaction would be more like leaving messages for distant descendants than having a conversation with contemporaries. Alcyoneus's 16 million light-year size makes communication even more improbable. If civilizations existed on opposite ends of the radio lobes, they might never know about each other. The light travel time exceeds the typical lifetime of stars, and perhaps the lifetime of civilizations themselves. These vast structures force us to confront profound questions about our place in the cosmos. Are we alone? Is intelligence common or rare? If life is common, why have we not detected any evidence of it? These questions, collectively called the Fermi paradox, become even more puzzling when contemplating galaxies like IC 1101. With so many stars and so much time, where is everyone? The answer might be simpler than we think. Maybe we live in a universe where the next record-breaking discovery is always waiting. Alcyoneus holds the current record at 16 million light-years. IC 1101 contains 100 trillion stars. These measurements represent the largest structures we have found so far. But the universe is vast, and our surveys remain incomplete. Most of the sky has never been observed at the sensitivity needed to detect structures like Alcyoneus. Somewhere out there, something larger is waiting. Radio surveys have mapped only a fraction of the sky. The low-frequency array that discovered Alcyoneus focused on the northern sky, leaving the southern hemisphere less explored. Other radio galaxies might extend even farther but remain undetected because they lie in regions not yet surveyed. As telescopes become more sensitive and surveys more complete, larger structures will emerge from the data. Optical surveys face similar limitations. Observing IC 1101's faint outer halo required extremely deep exposures, the kind that exist for only a tiny fraction of known galaxies. Most galaxies have only shallow observations that capture the bright core but miss the extended halo. Deeper surveys might reveal that many large elliptical galaxies are actually bigger than currently measured. IC 1101 might lose its stellar size record when astronomers observe other supergiants with comparable sensitivity. The universe contains roughly 2 trillion galaxies in the observable volume. We have studied in detail perhaps a few million. That leaves over 1,999,000,000,000 galaxies barely explored. Statistical arguments suggest that if the universe is large enough and surveys incomplete enough, larger structures must exist. We simply have not found them yet. The current record holders might represent barely above average examples, not true extremes. Future telescopes will revolutionize our census of cosmic structures. The Square Kilometre Array will detect radio galaxies across the entire sky with unprecedented sensitivity. The James Webb Space Telescope, already operational, peers deeper into the distant universe than any previous instrument. The extremely large telescope, under construction in Chile, will have a mirror 39 meters across, capturing more light than any existing optical telescope. These instruments will find structures that make Alcyoneus and IC 1101 look small. But there are theoretical limits. Galaxies cannot grow arbitrarily large. The universe's age and dark energy's acceleration impose maximum sizes. Computer simulations suggest structures larger than about 20 to 30 million light-years become improbable. Beyond that scale, expansion pulls material away faster than gravity can assemble it. Alcyoneus at 16 million light-years approaches this theoretical limit. Finding something much larger would challenge our understanding of cosmic structure formation. Yet scientists have been wrong before. Every time we thought we found the limit, nature surprised us. Black holes turned out more massive than theory predicted. Galaxies formed earlier than models suggested. The universe kept revealing phenomena that forced us to revise our thinking. Alcyoneus and IC 1101 already push against theoretical boundaries. Perhaps something exists beyond those boundaries. Something so extreme it requires new physics to explain. The search continues. New telescopes turn on. New surveys begin. Astronomers process petabytes of data, searching for anomalies, outliers, and record breakers. Every year brings discoveries that reshape our understanding. The largest galaxy ever found is simply the largest galaxy ever found so far. And when that record falls, when something larger emerges from telescope data, it will force us once again to confront how little we truly understand about the cosmos. We measure the unmeasurable. We count the uncountable. We map the infinite. These giant structures humble us, reminding us that no matter how much we learn, the universe always has something bigger, stranger, and more impossible waiting just beyond the edge of our knowledge. The biggest galaxy we have discovered is bigger than your imagination. But your imagination will need to grow again when the next record shatters. IC 1101 is not sitting still. Nothing in the universe stays motionless. The galaxy races through space at approximately 1.4 million miles per hour. That velocity seems impossible until you realize that everything around it moves at similar speeds. Our own galaxy travels at over 1 million miles per hour through the cosmic web. Motion is universal. Stillness does not exist. The motion comes from multiple sources acting simultaneously. First, IC 1101 orbits within its galaxy cluster. The cluster's gravity pulls it in complex patterns around the cluster center. Sometimes the galaxy moves toward the core, sometimes away, following an orbit that takes hundreds of millions of years to complete. This orbital motion contributes several 100,000 miles per hour to IC 1101's total velocity. Second, the entire Abell 2029 cluster moves through space. Galaxy clusters drift along cosmic web filaments, flowing like rivers from voids toward denser regions. The cluster's motion through the cosmic web adds another several 100,000 miles per hour to IC 1101's speed. This component of motion reflects the large-scale structure of the universe, the way matter organizes itself into filaments, walls, and voids. Third, the universe itself expands. Space between galaxy clusters grows continuously, carrying them apart. This expansion adds to IC 1101's apparent velocity when measured from Earth. The farther away an object sits, the faster expansion makes it recede. At IC 1101's distance of 1 billion light-years, expansion contributes approximately 50,000 miles per hour to its motion away from us. Scientists measure these velocities using the Doppler effect. When an object moves toward you, its light shifts toward shorter, bluer wavelengths. When it moves away, light shifts toward longer, redder wavelengths. By measuring how much spectral lines shift from their rest wavelengths, astronomers calculate velocity. IC 1101 shows a redshift, indicating it moves away from Earth at roughly 50,000 miles per hour due to universal expansion. But this measurement includes all motion components combined. Separating the different velocity components requires careful analysis. Astronomers must account for our own motion. Earth orbits our star at 67,000 miles per hour. Our star orbits the galactic center at 490,000 miles per hour. Our galaxy moves toward Andromeda at 70,000 miles per hour. The local group of galaxies, including ours and Andromeda, moves toward the Virgo cluster at 860,000 miles per hour. All these motions affect measurements of distant objects. After accounting for all these factors, astronomers determine IC 1101's peculiar velocity, its motion relative to the average expansion of the universe. This peculiar velocity reflects the galaxy's response to gravity from nearby massive structures. The galaxy falls toward over-dense regions and away from under-dense voids. These gravitational flows sculpt cosmic structure over billions of years. The velocities involved are staggering by human standards but typical for cosmic scales. Everything moves fast. The universe knows no rest. Even something as massive as IC 1101, weighing 1 quadrillion times our star's mass, gets tossed around by gravity like a leaf in a stream. But velocity alone does not capture how extreme these environments are. The temperatures inside these galaxies would instantly vaporize anything we know. The space between stars in IC 1101 is not cold and empty. Hot gas fills the galaxy, heated to millions of degrees by processes that would annihilate matter instantly. This superheated plasma shines brightly in X-ray wavelengths invisible to human eyes. If you could see X-rays, IC 1101 would glow with intense radiation, far brighter than its visible light. The gas reaches temperatures around 10 million degrees Kelvin. At this temperature, atoms cannot exist. Electrons get stripped from their nuclei, creating a plasma of free-floating particles. The plasma emits X-rays through thermal radiation and through interactions between fast-moving electrons and ions. Observing these X-rays tells astronomers about conditions inside the galaxy that optical telescopes miss completely. Where does this heat come from? Several sources contribute. When smaller galaxies merge with IC 1101, the collision compresses gas, converting kinetic energy into heat. The infalling galaxies slam into IC 1101 at speeds of several million miles per hour. The impact shocks the gas, heating it to extreme temperatures. This process, repeated thousands of times over billions of years, pumped enormous thermal energy into the galaxy. The central supermassive black hole also heats surrounding gas. As matter spirals into the accretion disk, friction heats it to billions of degrees near the black hole. Some of this energy radiates outward, warming gas throughout the galaxy. The jets shooting from the black hole's poles dump additional energy into the surrounding medium. When jets plow through the gas, they create shock waves that heat material along their path. Supernovae contribute as well. When massive stars explode, they release more energy than our star will emit in its entire lifetime. Each supernova heats surrounding gas and accelerates particles to incredible speeds. With trillions of stars in IC 1101, supernovae explode constantly, even in this aging galaxy. Older stars that formed billions of years ago are now reaching the ends of their lives and detonating. Each explosion adds more heat to the intergalactic medium. The hot gas glows in X-rays, but contains relatively little mass. Despite temperatures in the millions of degrees, the gas remains extremely diffuse. The density is far lower than the best vacuum achievable on Earth. A cubic foot of this hot gas contains fewer particles than a cubic foot of Earth's upper atmosphere. The high temperature comes from particles moving very fast, not from high density. This hot atmosphere has consequences. It prevents new star formation throughout the galaxy. For stars to form, gas must cool to about 10,000 degrees or less and collapse into dense clouds. But the hot gas cannot cool efficiently. Thermal energy keeps it puffed up and diffuse. Any cold gas that tries to settle into the galaxy gets heated by mixing with the surrounding hot plasma. This negative feedback helps explain why IC 1101 stopped forming stars billions of years ago. Alcyoneus's jets heat gas to even more extreme temperatures. Near the black hole, temperatures exceed 1 billion degrees. The jets themselves carry plasma heated to hundreds of millions of degrees and accelerated to 98% light speed. When this material slams into surrounding gas, the collision creates shocks with temperatures reaching billions of degrees. The universe routinely produces temperatures we can barely comprehend. These extreme temperatures remind us that space is not the cold, empty void we imagine. In massive galaxies like IC 1101, the environment between stars is hellishly hot, a furnace that would vaporize planets instantly. But if you could somehow survive the heat and fall toward the center, you would encounter something far more terrifying than mere temperature. Imagine falling toward IC 1101's black hole. You start far away, where the black hole's gravity feels weak. You drift inward, slowly at first. As you approach, gravity strengthens. You accelerate. Within a few million miles, you move faster than any rocket humanity ever built. But you have barely begun your descent. The black hole weighs 70 billion times our star's mass. Its event horizon, the boundary beyond which nothing escapes, stretches across a diameter larger than our entire solar system. The event horizon for this monster measures roughly 140 billion miles across. Pluto orbits our star at about 3.7 billion miles. The black hole's event horizon is nearly 40 times wider than Pluto's orbit. This thing could swallow our solar system and barely notice. As you fall closer, tidal forces begin tearing you apart. Your feet feel stronger gravity than your head because they are slightly closer to the black hole. This difference creates a stretching force called spaghettification. For smaller black holes, spaghettification becomes lethal far outside the event horizon. But IC 1101's black hole is so massive that tidal forces remain relatively weak at the event horizon. You could theoretically cross the event horizon intact. Time behaves strangely near black holes. As you fall inward, clocks on your body tick normally from your perspective. But observers watching from far away see your clock slow down. The closer you get to the event horizon, the slower you appear to move from their perspective. At the event horizon, time dilation becomes infinite. Observers would see you freeze, taking infinite time to cross. But you experience no such delay. You plunge through in finite time. Once past the event horizon, return becomes impossible. Every direction points inward. Space itself curves so severely that all paths lead to the singularity at the center. You cannot turn around. You cannot fire rockets to escape. The concept of escape loses meaning. You have entered a region of space-time disconnected from the outside universe. The fall continues. Inside the event horizon, tidal forces strengthen rapidly. Even IC 1101's massive black hole eventually tears you apart. Your body stretches lengthwise while compressing horizontally. The forces become unbearable. You disintegrate into atoms, then subatomic particles. The particles themselves might break down into components we do not yet understand. Eventually, you reach the singularity, the black hole's core, where density becomes infinite and physics breaks down. General relativity predicts the singularity exists but cannot describe what happens there. The mathematics produces infinities that signal the theory's incompleteness. We need quantum gravity, a theory we have not yet developed, to understand singularities. They represent gaps in human knowledge. But here is the disturbing part. From the outside universe's perspective, you never finish falling. Time dilation means observers see you asymptotically approach the event horizon, but never quite reach it. Your image freezes at the edge, redshifted and dimmed, slowly fading as photons struggle to escape the intense gravity. To the outside universe, you hang at the event horizon forever. But from your perspective, you crossed in seconds and met oblivion at the singularity moments later. Black holes create paradoxes that challenge our understanding of reality. Information falling into a black hole appears to be destroyed, violating quantum mechanics' principle that information is conserved. This information paradox remains unsolved despite decades of theoretical work. Black holes sit at the intersection of gravity and quantum mechanics, two theories that do not yet work together. They represent the universe testing us. IC 1101's black hole has swallowed countless stars, planets, and clouds of gas over billions of years, all that matter compressed into the singularity or radiated away as energy. The black hole grew fat on this diet, becoming one of the most massive objects in the universe. And surrounding this monster, invisible fields stretch across distances that dwarf the black hole itself. Magnetic fields permeate Alcyonius, threading through its 16 million light-year span. These fields are not the weak magnetism you experience with refrigerator magnets. They organize cosmic-scale structures, control the flow of matter, and confine particles traveling near light speed. Understanding these fields reveals how Alcyonius maintains its coherent structure across such impossible distances. The fields originate near the black hole's accretion disk. As matter spirals inward, it drags magnetic field lines along, twisting them into complex configurations. The spinning black hole amplifies these fields through a dynamo effect similar to how Earth generates its magnetic field, but incomparably more powerful. Near the black hole, magnetic field strength exceeds anything we can create in laboratories by factors of trillions. These intense magnetic fields shape the jets. They act like invisible pipes, channeling plasma away from the accretion disk and preventing it from dispersing. Without magnetic confinement, the jets would spread out and fade within thousands of light years. But the fields keep them collimated, maintaining narrow beams across millions of light years. The fields also accelerate particles within the jets, flinging electrons and protons to 98% light speed. As the jets expand into the radio lobes, magnetic fields expand with them. The fields in the lobes are much weaker than near the black hole, but they still exceed Earth's magnetic field by factors of thousands. These fields trap high-energy electrons spiraling around field lines. The electrons cannot escape. They remain confined within the lobes, continuously emitting synchrotron radiation that makes Alcyonius visible in radio wavelengths. The field strength decreases gradually from the jet base to the lobe edges. Near the black hole, fields might reach millions of Gauss. 1 Gauss equals Earth's surface magnetic field strength. At the lobe edges, field strength drops to micro-Gauss levels, comparable to the magnetic fields in the space between galaxies. This gradual decrease allows the jets to expand smoothly without losing coherence. Magnetic fields also interact with the surrounding intergalactic medium. As jets plow through ambient gas, they compress the magnetic fields already present. This compression creates shock waves in both the gas and the magnetic field. The shocked regions emit additional radiation, creating complex structures visible in detailed radio maps. Astronomers use these structures to trace how jets interact with their environment over time. The total magnetic energy stored in Alcyonius's lobes is staggering. Rough estimates suggest the equivalent of millions of stars' worth of mass energy converted entirely into magnetic fields. This energy accumulated over hundreds of millions of years as the jets continuously pumped it into the lobes. The fields store this energy like cosmic batteries, slowly releasing it as trapped particles radiate away their energy. Scientists study these magnetic fields using polarization measurements. Radio waves from synchrotron emission are polarized, meaning the electric field oscillates in a preferred direction. The polarization direction traces magnetic field orientation. By mapping polarization across Alcyonius, astronomers reconstruct the three-dimensional magnetic field structure. The fields show organized patterns consistent with jet-driven outflows, confirming the connection between the central black hole and the distant lobes. Understanding cosmic magnetic fields remains challenging. We cannot see them directly. We infer their properties through effects on visible matter and radiation. But those inferences reveal a universe threaded with magnetism, organizing structure on the largest scales. Yet these magnetic fields, powerful as they are, confine something we can barely see through the distortions of cosmic time. When you observe distant galaxies, you see not their current state, but ancient light from when they were young. The farther you look, the further back in time you see. Alcyonius sits 3 billion light-years away, meaning we observe it as it appeared 3 billion years ago. IC 1100, and one lies over 1 billion light-years distant, showing us its billion-year-old self. But astronomers have found infant versions of such galaxies in the very distant universe, revealing how these monsters formed. The most distant galaxies we observe existed less than 1 billion years after the Big Bang. Light from them has traveled for over 13 billion years to reach us. We see them as they appeared when the universe was young, small, and very different from today. These early galaxies look nothing like IC 1101. They are compact, irregular, and filled with active star formation. They represent the building blocks that eventually assembled into giants. The James Webb Space Telescope, launched in late 2021, specializes in observing these ancient galaxies. Its infrared instruments can detect the light from the first generation of galaxies, redshifted by expansion into wavelengths invisible to previous telescopes. Early results revealed galaxies forming stars at prodigious rates less than 500 million years after the Big Bang. These galaxies look like they are rushing to build stellar populations as quickly as possible. Over billions of years, these small early galaxies merged together. Each merger added mass, stars, and gas. Computer simulations show how hierarchical assembly builds large galaxies from small ones. The process resembles evolution, with smaller structures combining into progressively larger ones. A galaxy like IC 1101 represents the endpoint of this process, the product of countless mergers over cosmic time. Astronomers find evidence of this assembly history by studying galaxy populations at different distances. Nearby galaxies like IC 1101 are old and massive. Galaxies at moderate distances, a few billion light-years away, show intermediate properties. Very distant galaxies appear young and small. This progression traces cosmic evolution. The universe grew its large galaxies over time through mergers and accretion. But some distant galaxies puzzle astronomers. A few massive elliptical galaxies existed surprisingly early, less than 3 billion years after the Big Bang. These galaxies appear fully formed, with large stellar masses and low star formation rates similar to IC 1101. How they assembled so quickly remains mysterious. Standard models suggest building something that massive should take longer. Finding them challenges our understanding of early universe processes. These ancient observations also show when giant radio galaxies like Alcyoneus first appeared. Radio galaxies existed throughout cosmic history, but the largest ones formed relatively recently. Most giant radio galaxies, with lobes exceeding several million light-years, are found in the nearby universe, less than 5 billion light-years away. This suggests such extreme structures require billions of years to develop and maintain. Observing galaxy evolution across cosmic time reveals that the universe changes. The early universe was more chaotic, with higher merger rates and more active star formation. The modern universe is calmer, with lower star formation rates and fewer violent interactions. This transition occurred gradually over billions of years. We live in a mature universe where the most extreme structures have already formed. Every image of a distant galaxy is a time machine, showing us the past. The universe provides a natural fossil record written in starlight. By observing galaxies at different distances, astronomers reconstruct the history of cosmic structure formation from the Big Bang to today. The story revealed is one of gradual assembly, violent mergers, and continuous growth. Yet when we calculate the actual matter density in these seemingly solid structures, we discover something shocking about how empty they truly are. IC 1101 contains 100 trillion stars spread across 6 million light-years. That sounds incredibly dense until you calculate the actual numbers. The average density of IC 1101 is lower than the air you breathe. Despite containing more stars than we can count, the galaxy remains mostly empty space. Understanding this emptiness reveals how diffuse the universe really is at all scales. Consider the volume first. Approximate IC 1101 as a sphere, 6 million light-years in diameter. Calculate the volume using basic geometry. The result exceeds 100 million cubic light-years. Now divide the number of stars by this volume. You get roughly 1,000 stars per cubic light-year. That sounds like a lot until you realize a cubic light-year contains an incomprehensibly huge volume. 1 light-year equals about 6 trillion miles. A cubic light-year contains 6 trillion times 6 trillion times 6 trillion cubic miles. That equals roughly 210 quintillion cubic miles. With 1,000 stars per cubic light year, the average spacing between stars is hundreds of trillions of miles. The nearest star to our own sits about 4 light-years away. In IC 1101's core, stars cluster more densely, but even there, distances between stars dwarf the stars themselves. Our star has a diameter of about 860,000 miles. The nearest star is 25 trillion miles away. The ratio is nearly 30 million to 1. If you shrunk our star to the size of a basketball, the nearest star would be 4,000 miles away. Most of the galaxy is empty space. IC 1101 is no different. Despite having 100 trillion stars, the overwhelming majority of its volume contains nothing but extremely diffuse gas and dark matter. The average mass density in IC 1101 is approximately 1 hydrogen atom per 10 cubic feet. For comparison, Earth's atmosphere at sea level contains about 10 to the power 25 atoms per cubic foot. The best vacuum chambers on Earth achieve densities around 1 million atoms per cubic foot. IC 1101's average density is 1 billion times lower than our best laboratory vacuums. By any standard, the galaxy is nearly empty. The dark matter halo has even lower density. Dark matter spreads across hundreds of thousands of light-years surrounding the visible galaxy. The dark matter density in outer regions drops to approximately 1 particle per several thousand cubic feet. We cannot measure this directly since dark matter is invisible, but gravitational effects reveal its presence and distribution. Even IC 1101's core, the densest region, remains mostly empty. The core contains the highest concentration of stars, but even there, stellar collisions almost never occur. Stars pass within light-years of each other without interacting. The gravitational perturbations might alter orbits slightly, but actual physical collisions require extraordinarily unlikely alignments. In the galaxy's entire history spanning billions of years, perhaps only a few thousand stellar collisions occurred among 100 trillion stars. This emptiness applies everywhere. Galaxy clusters contain mostly empty space. The cosmic web filaments are nearly vacant. Even atomic nuclei are mostly empty space, with electrons orbiting far from the nucleus compared to particle sizes. Emptiness dominates at all, scales from atoms to galaxy superclusters. Yet this emptiness is precisely what allows structures to grow so large. If matter was more densely packed, gravitational interactions would be more frequent, mergers would happen faster, tidal forces would be stronger. The delicate balance between gravity pulling structures together and motion keeping them apart would shift. Perhaps universes with higher densities cannot form structures as large as IC 1101. Perhaps the vast emptiness is necessary for extreme scale. These density calculations force us to confront what galaxies really are. They are not solid objects. They are statistical concentrations of matter in an otherwise nearly empty universe. The brightest, most massive structures we observe remain primarily void, but assembling even these sparse structures from the primordial universe required timescales that challenge comprehension. Building a galaxy like IC 1101 requires billions of years. The process begins shortly after the Big Bang, when tiny density fluctuations in the early universe grow through gravitational attraction. These fluctuations start as quantum fluctuations during cosmic inflation, a brief period of exponential expansion in the universe's first fraction of a second. Those microscopic variations in density grow into galaxies, galaxy clusters, and the cosmic web itself. The first stars formed roughly 180 million years after the Big Bang. Before this period, called the Cosmic Dark Ages, the universe contained only hydrogen, helium, and dark matter. No stars, no galaxies, just diffuse gas slowly collapsing under gravity. When the first stars ignited, they lit up the universe. ending the Dark Ages. These first stars were massive, burning hot, and dying quickly as supernovae within a few million years. The first small galaxies assembled between 200 million and 500 million years after the Big Bang. These proto-galaxies contained millions to billions of stars, tiny compared to IC 1101, but representing the first organized structures. They formed where dark matter clumped most densely, providing gravitational wells for normal matter to fall into. These early galaxies merged frequently, growing larger through collisions. By 1 billion years after the Big Bang, galaxies with masses comparable to our Milky Way existed. These galaxies had spiral structures and active star formation. They represent intermediate steps in the assembly process. Over the next several billion years, these galaxies continued merging, building progressively larger structures. The universe's merger rate peaked around 3 to 4 billion years after the Big Bang, when galaxies were packed more closely together and collisions happened frequently. IC 1101 likely began forming around 2 to 3 billion years after the Big Bang. It started as one of the more massive early galaxies in a dense region destined to become a galaxy cluster. Over the next 8 to 9 billion years, it absorbed hundreds or thousands of smaller galaxies. Each merger added mass and heated the stellar population, gradually transforming it from a star-forming spiral into a passive elliptical. The galaxy's growth rate was not constant. It experienced periods of rapid growth during major mergers, alternating with quieter periods of slow accretion. The most violent episodes occurred between 5 and 8 billion years after the Big Bang, when large galaxies collided with IC 1101's growing structure. These major mergers triggered intense starbursts, creating billions of massive stars in relatively short periods. By about 7 billion years after the Big Bang, roughly 6.8 billion years ago, IC 1101 probably reached most of its current mass. Star formation declined as the galaxy exhausted its gas supply. The central black hole grew to its current enormous size through mergers with black holes from consumed galaxies. The galaxy transitioned from active growth to passive evolution, maintaining its size while slowly fading as its stellar population aged. Alcyoneus's 16 million light-year radiolobes required several hundred million years to inflate. The jets must have remained active continuously for this entire period. This suggests the black hole maintained a steady fuel supply for hundreds of millions of years, fed by gas flowing along cosmic web filaments. Interrupting the fuel supply even briefly would shut down the jets and halt lobe expansion. The timeline reveals that structures like IC 1101 and Alcyoneus are products of nearly the entire history of the universe. They formed through processes beginning shortly after the Big Bang and continuing for over 13 billion years. We observe them near the end of their growth phase, having accumulated most of their mass and reached their maximum sizes. Future evolution will be gradual. IC 1100 and one might absorb a few more small galaxies, but major growth is unlikely. Alcyoneus's jets will probably shut down within the next few 100 million years as the fuel supply dwindles. These giants represent the end result of cosmic structure formation. They are among the final products the universe will create at this scale. Yet, IC 1101 and Alcyoneus are not alone at the top. Other galaxies compete for supremacy in different categories. IC 1101 and Alcyoneus dominate size records, but other galaxies hold their own extraordinary distinctions. The universe contains many types of extremes, and different galaxies excel in different categories. Understanding these other record holders reveals the diversity of cosmic structures and the many ways galaxies can push against physical limits. UGC 2885, nicknamed the Rubin Galaxy, holds the record for the largest spiral galaxy. It stretches 832,000 light-years across, 8 times wider than our Milky Way. Unlike IC 1101's featureless elliptical form, this galaxy shows beautiful spiral structure with well-defined arms. It rotates majestically, containing roughly 10 times as many stars as our galaxy. The galaxy is so large that astronomers initially thought it must be two galaxies overlapping, but observations confirmed it is a single massive spiral. M87 hosts one of the most massive black holes ever measured. The black hole weighs approximately 6.5 billion times our star's mass, confirmed through Event Horizon Telescope observations that produced the first ever image of a black hole's shadow. While smaller than IC 170 billion solar mass monster, M87's black hole is better studied and produced the iconic black hole image that appeared in media worldwide in 2019. The brightest galaxy in the universe is W24600526, a distant dusty galaxy discovered by the WISE Space Telescope. It shines with the light of 350 trillion stars, powered by an extremely active central black hole. The galaxy is consuming matter so rapidly that it generates tremendous luminosity across all wavelengths. This brightness record likely represents a temporary phase in the galaxy's evolution, rather than a permanent state. The most distant galaxy currently known is HD1, observed as it appeared roughly 13.5 billion years ago, only 330 million years after the Big Bang. This galaxy shows extremely active star formation and might host some of the first generation of stars ever formed. Observing it provides a window into the early universe when galaxies were just beginning to assemble. The galaxy with the highest star formation rate is COSMOSAZTEC1, creating approximately 1,000 times our star's mass in new stars every year. For comparison, our Milky Way creates about 2 to 3 times our star's mass annually. This starburst galaxy is consuming its gas supply at an unsustainable rate, suggesting it will exhaust its fuel within a few 100 million years and transition to a passive state like IC 1101. Segway 2 holds the opposite extreme as the faintest galaxy ever discovered. This dwarf galaxy contains only about 1,000 stars total, making it barely more than a large star cluster. Its survival as a distinct galaxy depends on a significant dark matter halo providing gravitational binding. Without dark matter, such a small collection of stars would disperse quickly. The most isolated galaxy known is MCG +0102015, sitting roughly 100 million light-years from its nearest neighbor. This galaxy evolved in near-total isolation, never experiencing the mergers and interactions that shape most galaxies. Studying it reveals what happens when galaxies develop without external influences. Hoag's object represents the most perfectly formed ring galaxy, with a circular ring of stars surrounding a central core with almost nothing between. The ring and core appear completely separated, creating a bizarre appearance unlike typical galaxies. The formation mechanism remains debated, but likely involved a rare type of collision that stripped stars into a perfect ring configuration. Each record holder teaches us something different about galaxy formation and evolution. Extremes reveal the boundaries of what physics allows. They test our theories and force us to explain how nature creates such diverse structures. IC 1101 and Alcyoneus earn their fame through sheer size, but the universe offers countless other ways to be extraordinary. And all of these record holders, magnificent as they are today, face inevitable decline in the deep future. IC 1101 and Alcyoneus will not last forever. Nothing does. Over the next trillion years, these cosmic giants will fade, their stars dying one by one, until only darkness remains. Understanding their future reveals the ultimate fate awaiting all galaxies and provides a glimpse of what the universe will become in the incomprehensibly distant future. In the near term, meaning the next few billion years, IC 1101 will continue absorbing small galaxies from its cluster. It will grow slightly more massive, perhaps reaching 1.1 or 1.2 quadrillion times our star's mass. But this growth will be minor compared to its current size. The major growth phase ended billions of years ago. The galaxy now exists in slow decline, gradually consuming nearby material but fundamentally unchanging. Star formation will not resume. The galaxy already exhausted its cold gas supply. Even cannibalized galaxies contribute mostly stars rather than gas. Any gas added from mergers will be shock-heated to millions of degrees, too hot to collapse and form stars. IC 1101 will remain a collection of aging stars burning through their remaining fuel with no replacements coming. The most massive stars still burning in IC 1101 will die within the next few billion years. These stars exhaust their fuel quickly, exploding as supernovae or collapsing into black holes. As they disappear, the galaxy's average luminosity will decrease. Fewer bright stars means less total light output. The galaxy will grow dimmer and redder as its stellar population ages. By 1 trillion years from now, all stars more massive than about 1/10 our star's mass will have died. Only small red dwarf stars will remain, dim embers barely glowing in the darkness. These stars burn so slowly they can last for trillions of years, but they provide very little light. IC 1101 will be a ghost galaxy, containing 100 trillion dead stellar remnants, white dwarfs, neutron stars, and black holes plus whatever dim red dwarfs still burn. Alcyoneus's jets will shut down long before this. The black hole will exhaust its fuel supply within a few 100 million years. Without continuous energy input, the radio lobes will fade, their trapped electrons radiating away their energy. Within a few billion years, the lobes will be invisible, leaving only the central elliptical galaxy. Alcyoneus will cease being a radio galaxy, becoming just another fading elliptical. By 100 trillion years from now, even the longest-lived red dwarf stars will die. IC 1101 will contain only stellar remnants. No fusion will occur anywhere in the galaxy. The only energy sources will be occasional black hole accretion events when a star or planet accidentally falls into one of the galaxy's billions of stellar mass black holes. These accretion events will be rare, providing brief flashes of light in an otherwise dead galaxy. Dark energy will continue accelerating cosmic expansion. By 100 trillion years, the universe will have expanded so much that only gravitationally bound structures remain visible. Individual galaxy clusters will be isolated, unable to see other clusters as they recede beyond the cosmic horizon. IC 1101 will exist in a universe that appears to contain only its own cluster and nothing else. Eventually, even the galaxy itself will evaporate. Over timescales of 10 to the power 19 years, gravitational interactions between stellar remnants will occasionally eject objects from the galaxy. These close encounters give some objects enough energy to escape, leaving the galaxy and wandering into intergalactic space. Over unimaginable timescales, this process will disperse the galaxy completely. IC 1101 will not exist as a coherent structure. Its remnants will scatter across space. The black holes will be the last survivors. Stellar mass black holes will persist for 10 to the power 67 years. IC 1101 supermassive black hole, weighing 70 billion times our star's mass, will survive even longer, approximately 10 to the power 98 years. Eventually, even black holes evaporate through Hawking radiation, a quantum process that slowly converts black hole mass into particles. When the last black holes finally evaporate, nothing will remain of IC 1101, except scattered subatomic particles spreading through an ever-expanding void. This is the fate awaiting all structures in an accelerating universe. Expansion wins eventually. Everything disperses. Energy spreads thinner and thinner until the universe reaches maximum entropy, a state of perfect uniformity where nothing interesting can ever happen again. This end state, called heat death, lies in the incomprehensibly distant future, so far ahead that writing out the timescale in years would require 100 digits. But we do not live in that far future. We live in the age of galaxies, when structures like IC 1101 and Alcyoneus shine brightly against the darkness. We exist at the perfect time to observe the universe at its most interesting, filled with giant galaxies, active black holes, and ongoing structure formation. In another trillion years, astronomers in whatever civilizations still exist will look out at a much emptier universe, wondering if anything else exists beyond their own galaxy cluster. For now, the giants remain. IC 1100, and one glows golden, with the light of 100 trillion dying stars. Alcyoneus stretches its radio lobes across 16 million light-years, pumping energy into space at rates that dwarf stellar output. These cosmic monsters represent the peak of what the universe can build. And somewhere out there, perhaps in a region we have not yet surveyed, something even larger waits to be discovered. The universe always has one more surprise. The next record will fall. Another titan will emerge from telescope data, and once again we will be forced to expand our imagination to encompass scales we thought impossible. The biggest galaxy we have discovered is bigger than your imagination, but your imagination will need to grow again. It always does. The universe insists on it.